Right. Welcome to Thursday, week 5. How weird is it? It does not feel like we're almost halfway done. I swear it feels like we just started. This has really flown by, and it's because I'm enjoying myself. I love that you guys are interactive, and this is really amazing. So I love binomial probability distributions. I can tell you that when I first started teaching stats and when I first took stats, it was hard for me to wrap my brain around a usefulness of it. And a lot of it was because when I first took stats, I had no idea what I wanted to do. When I took stats, I still didn't know what my major was, what I was planning on doing. And so, because it was my very first term of college that I took this class. And it was actually with Fran Gunson, and it was during the summer. I remember that, my very first term of college. And so I had no idea what I wanted to do. So I didn't have ideas of like things I could do with this math. So I just kind of tucked it away. And as I became a teacher and started collecting data on different things, I started being able to use this to calculate probabilities of things happening and to kind of understand the world around me a little bit more. And it's actually kind of an amazing math. It's an amazing math. There's my English. I was actually started as an English major, believe it or not. So anyway, we're going to talk about what a binomial experiment is. Then we're going to compute probabilities of binomial experiments, and then look at the mean and standard deviation of them. And we're going to graph it. I'm never going to make you graph them, but we are going to graph them, graph one. So this is probably about the same length as yesterday or Tuesday's class. So it's not super long, but once again, if I put them both together, it would be way too long for one sitting. So we get a couple shorter things. And a lot of our lessons from here on out are going to be kind of like that, where it's going to be 2 shorter lessons in the week rather than one super long one. All right, so let's move on. So binomial experiment. So in order for something to be a binomial experiment, it has to have a fixed number of trials, So I have to perform the trial 10 times. So if I can say I chose 10 people at random, that is a fixed number of trials. The trials have to be independent. We already talked about what it means for things to be independent or dependent. We already talked about that. So the trials have to be independent. The outcome of one trial can't affect the outcome of other trials. So they have to be 2 mutually exclusive or disjoint outcomes. So we're looking at success or failure. Now, success and failure don't necessarily mean a good thing and a bad thing. It's just, here's the thing I'm looking for. Here's the thing I'm not looking for. That's all it is. That's what success and failure is. So then we need to have a fixed probability of success. So each trial has to have the same fixed probability of success. So this is how we determine if something is a binomial probability experiment. Now I'm going to give you a couple of examples so we can pick them apart and see what's wrong with them and things like that. So it will happen. We will do that. Give me a second to write things down. All right. Moving on. So notation that we use. So N, doggone it. This has this is my own fault. It is my own fault. My sleeve rubs on it, and there we go. Okay, so N is the number of trials. So however many trials we have, that's N, the number of trials. P is the probability of success. Therefore, 1 minus P is the probability of failure. So X would be the number of successes, how many successes we have. So if I randomly choose 5 people and 3 of them have red hair, my number of successes would be 3 if I was looking for redheads and not redheads. All right, let us take a look at some examples. Okay, we're going to determine whether these are binomial experiments, and if they're not, why they aren't. Okay, a player rolls a pair of fair die 10 times. The number X of sevens rolled is recorded. So I rolled a dice 10 times, the number of sevens. So our success is rolling a 7. So this is a binomial experiment. So our fixed number of successes, or fixed number of trials, there we go. This is the number of trials, 10 times. The probability of rolling a 7 is the same every time. And rolling a 7 one time is not going to make it so that I can't roll a 7 another time, or that it's more likely to roll a 7 another time. Unless you're like a gambler in Vegas or something, because people think that one thing affects the other, but we won't even go there. All right, let's look at the next one. The 11 largest airlines had an on-time percentage of 84.7 in November 2001. So in order to assess reasons for delays, an official with FAA randomly selects flights until she finds 10 that were not on time. The number of flights X has that need to be selected is recorded. So our number of successes X, or our number of successes, I don't know, the number that the last sentence doesn't even make sense to me. Anyway, this is not a binomial experiment. We don't have a fixed number of trials. So they kept selecting flights until they got 10. So we don't even know the number of trials. They could have had 23 trials. So they were looking for 10 successes, which is not on time. Their success, in this case, were not on time. So they kept going until they had 10 of them. So we don't have a fixed number of trials. Now, if they would have said they selected 100 flights at random and recorded the number that were not on time, now that would have been a binomial experiment. Let's do next one. In a class of 30 students, 55% are female. The instructor randomly selects 4 students. The number X of females selected is recorded. This one almost looks binomial. However, it is not, because the trials are not independent. Once I select one female and take her out of the class, there's only 29 students in class then. So or once I pull any student out, pull them out of the class, there's 29 students now. So it will no longer be 55% female. If my first one I pulled out was female, then it'll be a greater percent are male. If the first one I pull out is a male, then my percent of female will be higher. That makes sense. So now there's only 29 students. So the trials are not independent. The effect pulling out one affects the probability of the rest of them. All right. Is this one nope, this one we're now going to construct a binomial probability distribution. So 7% of people, woo! Oh, any questions on the first section on the determining if something is a binomial probability distribution? I don't know if there's any questions on the homework about that or not. I can't remember. Okay.
What was the question?
I wondered if there was any questions on the determining whether or not it was a binomial probability.
I don't believe so.
Okie dokie. Is today just a day where everybody's just kind of extra tired? Seems like all the students at school were that way and all the teachers are that way. It seems like it's just that kind of a day. Okay. According to the American Red Cross, 7% of the people in the US have type O negative blood. So we took a simple random sample. Woo, my whole iPad just fell. A random sample of 4 is obtained, and the number of people with type O blood negative is recorded. So we're going to construct a probability distribution for this variable. Now we're going to use a tree diagram, and you are going to see that it is going to go crazy. So what we're going to be looking at in the tree diagram is, so we could have our first person that we take could have either O negative or not O negative. Then based off of that, the second person you'll see, so first trial, the success would be has O negative, failure is not. So next trial, We build off of that. We either have O negative or don't have O negative. Guys do not need to write this down. I will not make you do a tree diagram. Don't worry, because you'll see why I would not make you do this. Though they are kind of
Thank
fun.
you.
You're welcome. But I wanted you to see how we build this. The point of doing the tree diagram is so you can see the math behind what your calculator is doing for you. And so I always like to do that so that you're not just plugging it into your calculator and having no idea what's happening behind the scenes. So that's the point of this. Then our third trial, success or failure can come off of each one. Fourth trial, be thankful we didn't have pull like 7 people out. Can you imagine what that would look like? And just think about, I had to put every single one of those little S's and F's on there and all those little arrows. That was fun. So here I have 4 successes. Notice one time I have 4 successes. And the number of time I have 3 successes is 1, 2, 3, 4. It looks like 4 times I have 3 successes. And there's a whole bunch of times I have 2 successes. These are all the different ways I could have successes and failures. So to have 2 successes, there's 1, 2, 3, 4, 5, 6 different ways. 1 success, 1, 2, 3, 4 different ways. 1 way to have 0 successes. So this is just the way that they can be the outcomes I can have, the possible outcomes. This is going to become important when we're actually doing the math for it and building our probability distribution. As I said, I am not going to require you to build one of these, just showing you the math behind it. All right. So we're going to compute the probability for each of the possible outcomes. So the probability of having 0 successes, this one was pretty easy. So the probability the first one is a failure, or sorry, 0 successes. Probability of the first one is a failure times the probability second is a failure, third is a failure, and fourth is a failure. Remember multiplication rule? All 4 of them have to be failures. So this is and the first and the second and the third and the fourth. So we're using our multiplication rule. So we got this for our probability. Gets a little more complicated when we do 1. So there's 4 different ways I can have 1 success. 4 different ways. So what I need to do is do my normal 3 failures and 1 success, but then multiply it by 4 because there's 4 different ways for this to happen. So that gives me my next probability. Same thing with my 2. There were 1, 2, 3, 4, 5, 6 different ways that I could have 2 successes. So I multiply by 6, my calculation, 2 failures, 2 successes. And then I'm just going to go down and build the rest of it. So this is my probability distribution right here. So it shows the probability of getting each of those. Questions on anything with me building that? I'm not going to make you build one of these either. I'm just showing you the math, as I said. And your calculator's going to do all the fun stuff for you. Okay. So this right here is the actual formula. And we're not going to go into that, how to use this formula. This is a combinatorics. It is basically counting rules. And so we are not going to do that. This right here, if we did it, this tells you how many different ways you can have a certain outcome. And this would be the probabilities, but we're not going to do this. So don't worry about that. Instead, we're going to use this right here. So on your calculator, you would hit second, then the VARS button, and then binom PDF. So second VARS binom PDF. And what's I going to say? So this right here is when we're looking for an exact number of successes. That's what we use this function right here for. Binom PDF is used when we have an exact number of successes. As we said before, the N is your number of trials. This is your probability. And then this is number of successes. And I know that there's a lot of like words like scrambled in or squished in there. Some of your calculators are going to have like spots for you to put them. Some of them won't. But it's okay. It's going to do the same math regardless. All right. I'm going to move on. I don't care about this. We're going to move on with this. Okay. So let's do some math here. According to Experian Automotive, 35% of all car owning households have 3 or more cars. In a random sample of 20 car owning households, we want to know the probability that exactly 5 have 3 or more cars. So 35% probability, we're taking a sample, a fixed sample of 20 cars, and we're looking for the probability exactly 5 have 3 or more cars. I'm going to swish over to my calculator. Maybe. So here's my calculator. In your fancy schmancy calculator, right? Hit second vars and scroll down to the first one. It's binom PDF. This is the binomial probability distribution function right here. This is for the exact number of successes, which we are looking for. Our number of trials, it was 20 because we took randomly took 20 people. Our probability is 0.35 because 35% of all households have 3 or more cars. Then we're going to look at our X value. Our X value is 5 because we're looking for the probability of exactly 5. If you don't have these spots to put things, I'm going to get, once it gets to my other screen, you'll see what the setup should look like. So if you don't have the spots to put things, you put the trials first, comma, then the probability, comma, and then your number of successes. If you don't have those little menu items to put things, then when you hit enter, it gives you a lovely probability. Questions? Right. So we got 12.72 or about 12.72%. So it's about a 12.72% chance that out of that we'd have 5 or more, exactly 5 people would have 3 or more cars out of 20 car owning households. Going to do another one, I believe. Why was that already have the answer? Oh, wait. Did it? Okay. It wasn't supposed to be on there yet. Ignore this. Ignore this. Okay. We're going to talk about the cumulative function. So the cumulative function, binom CDF, it is when we are doing less than. So if we're doing or less than or equal to. So our binom CDF, this function right here, is for less than or equal to. It gives a cumulative function. So if I use binom CDF for, and have looking at, put 5 in for successes, it will add together 5 successes, 4 successes, 3, 2, 1, and 0. So it is a cumulative function. Yes, this tells us how to do it, but I have learned that actually showing you is much better. So here it says random sample of 20 car owning households. We want to know the probability that less than 4 have 3 or more cars. So remember, the binom CDF function is less than or equal to, and it's less than 4. So 4 is not part of the group we're looking at. We're looking at less than or equal to 3. So if I 0, 1, 2, 3, 4, 4 is not part of it. We want these ones right here. So we're going to put 3 in for our binom CDF. I will show you on the calculator. Just remember the C means cumulative. That's how I always remember which one it is. And so every time I say binom CDF in my head, I'm thinking cumulative. So let's do the second vars and go down here to binom CDF. Our number of trials is 20. The probability of success is 0.35. Once again, we're looking for 3 or fewer, because 4 less than 4 is the same thing as 3 or fewer. If you don't have a calculator that has those inputs, this is what you would type in after the binom CDF. So your number of trials, your probability, and then the 3. And that gives us about 44.4%. It's weird that their number is different. Oh, wait, is that supposed to be? Okay, no, I was on the next screen. I was really confused. I don't know what happened to my animation. I don't know why it went away. The answers weren't supposed to pop up on my PowerPoints yet. My animation decided to run away. Oh, well, things happen. Questions so far? All right. So now we're going to do, so ignore all of this stuff. Ignore all of this so far. Ignore all of this. Don't look at it. Don't look at it yet. Just ignore it all. Okay. So now it wants, if
I have
it,
a question first.
yes.
Sorry.
No,
So
it's okay.
is the probability usually going to be in a percentage?
Yeah, they'll give it to you in a percent and you have to put it into a
In a
decimal.
percentage?
Yeah.
Okay.
Yeah, pretty much probably 95% of the time they will give you a percent. So,
Oh, that's cute. I like that. Okay.
and you can give your answer either way. I mean, my Open Math will tell you how to give your answer, but if you're taking my test, unless I specifically tell you, I don't really care how you give me the answer, or like on the handwritten homework, I don't really care how you give me the answer, as long as it's right. Just give me the right one, whatever that is. Yeah, I don't care, fractions, decimal, percent, whatever. Okay, so in this one, we want to know the probability of the at least 4 having 3 or more cars. So remember, our binom CDF does less than or equal to. So at least 4 cars, or at least 4 having 3 or more cars, means 4, 5, 6, 7, 8, all the way up to 20. So that is greater than or equal to. So I'm going to write these out. Just like 1, 1, 2, 3, 4, 5, 6, 7, etc. So we want this right here, but we don't have a function that can do that. So what I can do is I can find this and do 1 minus. So that'll basically be, it's the complement. So we're going to find everything that's not this right here. So that's what we're doing. So we're saying basically not less than or equal to 3. So we're going to do 1 minus our binom CDF. Remember, every time you see the word at least, use the complement rule. Every single time. If you see the word at least, use the complement rule. It's just have to be really careful what your number here is. Somebody saying something?
Sorry,
Question?
I'm muted, but my son's in the background.
Okay. That's
What
okay.
about at most? Is that the same as, would that be the same function as at least?
Well, at most, if I said like at most 4, isn't that the same thing as less than or equal to 4? Because at most 4 means it includes 4, 3, 2, 1, and 0. So at most would be less than or equal to. It's
But
only
if,
when you
oh.
see at least.
Uh,
Just go ahead.
so at most 4 would be like 0, 1, 2, 3, and 4.
Right. So it would
Okay.
be less than or equal to 4.
Thank you. I'm super sick in the net. So I'm trying to understand it to the best of my
Okay,
ability.
okay.
So at most would be like the last problem we
Yeah.
did.
Yes,
Okay.
this one right here, I could say at most 3, it would be the same question. What's the probability that at most 3 have 3 or more cars? Does that make sense?
Yeah, that kind of had me stopped up on the homework, a couple of questions that at most, because I was like, what is that?
Okay, I'm even more confused. I'm sorry.
Okay. So if you, okay, let's step away from these binomial things just for a second. Let's just talk wording. So if you moved in, let's say you moved into an apartment and you're a cat person. You love your cats. And the landlord says, yes, you can have cats, but you can only have at most 3 cats. Then you know that 3 is the maximum number of cats you have. You can have 0, 1, 2, or 3. So that's the same thing as less than or equal to 3 cats. But now if your landlord says, you know, I love cats too, and I know these cats don't want to be in there alone. So you can have cats, but you have to have at least 5 cats. Then you know that you can have 5 cats or more. You can't have less than 5 cats. Does that help at all? But please don't have at least 5 cats. I mean, you could if you wanted to, as long as you have lots of litter boxes or they're trained to ask to go outside.
That's a lot of cats.
It's a lot of cats. I have no cats. My daughter has 2 cats and she keeps sending me these pictures saying, isn't this cute? Should I get it? And I keep saying, no, you have 2 cats and 2 kids. The cats do not outnumber your kids.
Yes. When the cats outnumber the people, it becomes a lot of work.
I mean, her cats are great, but you know, I mean, I have dogs. I mean, you know, anyway. So the at most and at least, I know that it can be confusing. And if you need it, we do have a screen here. So if you need this, there's a this is on the PowerPoint. Woo, even though I don't think it says at most, does it? This would be, oh, it does. This says at most for less than or equal to. So this is a page in the PowerPoint. I usually just skip by it, but this is, if you wanted to, you can print off just this page. And this tells you which symbol to look for, and it might help you. I don't know. But this is a page in the PowerPoint. I just leave it in there, but I usually just skip on by. Okay, let's go back to the at least. We're gonna put this in the calculator. So at least 3 or more cars. I was gonna say cats. So as I said before, so 4, 5, 6. So we want this, but we don't have a function that'll give us that. So we need not this, not this. And remember, not this means calculate the probability of that, but then do 1 minus. So I'm going to do this in my calculator. Go back here. Boom. Okay, so I'm going to put in 1 minus and then do my binom CDF. Enter. And 20 trials. We're still on the same thing, but we're with the 1 minus on there. And we get about 95.6%. So you could, I mean, if you wanted to calculate I mean, I could have done this. I could have said 1 minus and then used my fancy schmancy copy and paste and done that. I mean, that works too. I love the copy and paste. That's my favorite thing. It is a game changer. It really is, because when you don't want to round mid calculations, you just can keep copying and pasting stuff in there. It's just awesome. Yeah. Okay. Sorry. Off my TI-84 fangirling here. Everybody keeps saying, you know, Texas Instruments, they've got the monopoly on it all, and it's terrible that they're running everything. And people, believe it or not, there is a whole community out there that loves to just bash Texas Instruments, but there's not anything better. I've tried a couple other ones and there's not anything better. There's a reason that everybody uses it. Okay, I'm done. No more fangirling for me. Okay, moving on. Questions on this one? And most of the stuff in the forums ends up being about the at least. And there will be 8 of them, and it's okay. Keep asking it until it clicks. Keep asking. I don't mind. You don't have to say, I'm so sorry for bothering you again. I don't mind at all. I really don't. Send me 12 emails. I don't care. My goal is to get you to get it. If it takes 12 emails and then it finally clicks, then I'm happy. Right. Moving on. Okay. I would like you to try these. I would like you to try these ones using Binom CDF or PDF, whichever one you're supposed to use. Remember, PDF is for an exact probability and CDF is for a cumulative probability. And letter D may stump you. If it does, just sit there and look pretty and we'll go through it together. But I'm going to do them in my own personal calculator, and then I'm just going to write answers. And if you get the same answers I do, then you'll be able to, then I can go over them afterwards. With 20 households, 41% chance they're wireless only. Yay, Holly, good job.
Okay, I've got my calculator stuck.
Uh-oh.
I only get for VARs 1 through 7.
You have to scroll down.
I am, and it just goes back up to the 1.
What kind of calculator do you have?
The 84 plus silver.
Okay, so,
I
okay,
had it a few minutes ago.
okay. So try shutting your calculator off and then turning it back on again first. Yay.
How do you shut it off? It's not going off.
You did second
Did
on.
Oh,
you-
second off. Okay, sorry. Okay, turn it on. Whoa.
Is it doing wonky things?
Press alpha F1 through F4 to locate shortcut menus. 1, do not show again. 2, continue.
They do not show again, and then see if you can get to it now.
Okay. Okay.
You're
Thank
good?
you.
Yeah.
I think so.
Just restarting a computer.
Wow. Wow.
It's okay. We got this. You're doing okay. It's good.
Okay, so let me do the first one at least,
Okay, no problem.
please.
And I'll walk you through them. So fewer than 3 can't be 3, right, Holly? At least 3 means 3 or more, right? Yes. It means you can have 3 cats. You can't have 2 cats. You guys are always going to remember that now, the whole cat thing.
Right. And do we go 4 digits after the decimal?
It doesn't, so
Always, or
in stats, there's no real rule. I usually go until I can get a percent and then 2 more. Is usually what I do. So like 99.72%, that's just usually what I do. There's no real rule. So the thing is, calculus has like a very, this is what you do. Stats, depending on what you're calculating, there's different rules. So I just usually go 4. I go 4. I didn't
Okay.
even go 4 significant figures. So, all right. How'd we do on the first one? Does anybody need me to go through the first one? So it should just be, I'm just gonna write it down because someone out in watching the Zoom recording land might need it. Whoops, this is PDF. Because remember, it's PDF if it is exactly, and it would be 20 households, 0.415. This is how you would set that up. I really think that that 41% is a lot more now. I highly doubt that there's only 41% of homes that are wireless only. I think it's higher, but that's just my guess. Okay, so fewer than 3. So we're looking at 3 doesn't count. So fewer than 3 would be 0, 1, or 2, right? So it's less than or equal to 2. Because I can only have fewer, I have to have fewer than 3 cats. So I can't have 3 cats. So now it's binom CDF because cumulative 20.413. Oops, 2. I lied to you. Don't do that. Don't write that down. There we go. 2. I say it and then I'm wrong. So as we already determined, at least 3 means 3 or more. So it's not 2 or fewer. So this would be 1 minus binom CDF 20.412. Is anybody able to get D? So, okay, good. So with D, what it's going to look like with D, I'm just going to put a few numbers. So 2, 3, 4, 5, whoops. And I am having issues. 6, 7, 8, 9. It decides to randomly change the color all by itself. So with this one, I am looking for these 3 values right here. I'm looking for those 3 values, the probability of just those 3. So the only 2 functions I have are the cumulative function or the function for the exact. We're definitely using a cumulative function. So what I need to do, because this is all I can do, is I can take the probability of 7 or fewer, right? Then I can subtract off what I don't need. So I would do 7 or fewer, and then I would subtract 4 or fewer. And that would give me my answer. So I'll write down what that looks like. So it's binom CDF 20.417 minus binom CDF 20.414. Because what I'm doing is I'm subtracting off that less than or equal to 4. And that will give me my 5 to 7. The other super tedious way to do this is to do exactly 7, exactly 6, and exactly 5, and then add the 3 things together. But that's more tedious. You could use PDF with 7, 6, and 5 and add them together. It'll give you the same answer. It's just tedious and not so fancy. All right, questions? Seems like a couple of you saying it's starting to click. That's awesome. Any questions? Okay. Move on. Okay. So with the binomial, the binomial random variable, we can calculate a mean and a standard deviation so we can get an expected value. So how many we would expect to have it. The mean is kind of self-explanatory. So if I have 20, I would multiply that 20 by the probability, and that's how many I would expect it to be. But if somebody's, I mean, if it's not any different than saying that somebody has $10,000 and I have 80% of what they have. Okay, well, I just multiply that by 0.8. I have $8,000. So it's just that math for getting the mean because it's an expected value. This is how many successes you would expect to get. So it's just the number of trials times the probability of success. That is your mean. Standard deviation is a little bit different. So standard deviation is the number of successes times the probability of success times the probability of failure, and then you take the square root of that. Standard deviation is always going to be funky. It's just the nature of the beast. So we just accept it and move on. He's our awkward little friend. That's me, by the way. I am the awkward little friend. All right, let's do some math with it. And so maybe this will help cement it. Okay. So according to Experian Automotive, 35% of all car owning households have 3 or more cars. In a simple random sample to 400 car owning households, we want the standard deviation and the mean that will have 3 or more cars. So for the mean, and this is just mu sub x, and this is just saying this is the mean of the x. So I would just take the number of trials we have, multiply it by 0.35. I'm going to use my fancy schmancy calculator. Oops, 400 times 0.35. And so this is 140. So we would expect out of 400 households, we would expect 140 of them to have 3 or more cars because that's 35% of 400. So for the standard deviation, to do 400 times 0.35 times 1 minus 0.35, which happens to be 0.65. You are more than welcome to put the 1 minus 0.35 in your calculator. It's not going to hurt anything. Just be really careful with your parentheses. So I usually do just put the whole thing in at once. You do it how you'd like. 0.35, 0.65. So here the standard deviation means exactly the same thing that it meant before. It still is, 1 standard deviation away. 68% of our samples of size 400 would have 140 cars, and 2 standard deviations away. 95% of our samples of 100, if I kept taking random samples of 400, 95% of them would have the mean within the 95 or within 2 standard deviations. So if I added 2 times 9.4, so approximately 160, approximately 120. So 95% of all samples of 400 would have between 120 and 160 or people who have 3 cars or more. So it means basically the same thing. And I don't think they ask you to interpret it. Can't remember, but I doubt it. Let's do another one or something similar. I think we have questions in a minute about that. So as you have a question like this on your quiz. So if we have a fixed probability of successes, as the number of trials increases, the probability will become more bell-shaped. You can't say this is always true because it is true if this. If NP times 1 minus P is greater than or equal to 10, then we can say that it is approximately bell-shaped. So you just might be asked, is it always true? You could say it is always true if this right here. That makes sense. This is going to come up over and over again, this NP times 1 minus P greater than or equal to 10. It's going to come up over and over again. What this means, this is actually the first time I've explained what it means because I finally really understand it, is that we have a big enough sample size so that we have an ample number of successes and failures to test this. So if I took a sample size of 3 people for something, that is not a very good sample size, and I'm not going to get enough successes and failures. So if I take larger sample size, it's going to be a better idea of the of representative of the population, basically. So you need larger sample sizes. So this right here, this math right here, it's kind of ensuring that your sample size is large enough to have a good representation of successes and failures. Basically what it's saying. Nobody's going to ask you that. I'm just trying to give you the meaning so you're not just thinking this is some arbitrary thing that's out there. All right. I only have 3 more slides. We are doing so awesome. So the empirical rule, we know what the empirical rule is, right? Where we draw that pretty little thing and do all of the 68 and 95 and yeah, so that's the empirical rule. So 95% of all observations will lie within 2 standard deviations of the mean. And anything less than 5% of the time is considered unusual. We already had this discussion before, but I am reinforcing this. If it occurs less than 5% of the time, it is considered unusual. All right. It goes with that whole outlier thing. I'm distracted by the cat. But I don't think you have 5 or more cats, right? Or 8 or more cats or whatever number we had.
No, I have 2 and that's plenty.
Okay. That was a pretty one though.
Yeah, that's Darcy.
Aw. Okay, sorry, I get distracted by cute pets on the cute pets and cute kids. They distract me. Okay. So we're going to determine if we have an unusual result here. There's going to be 2 different ways for us to determine this. I'm going to do it both ways, and you can choose what you like. Okay. So according to Experian Automotive, this is the same thing. So we conducted a simple random sample of 400 car owning households. We found that 162 had 3 or more cars. We want to know if this result is unusual. Yes, the math will pop up on my screen, but I don't want it to. I want to just do the math and talk you through it. So the first thing we're going to do is that right there, which we already did, and I didn't mean to do that. We have the NP. So we had the 0.35 times 400. We already looked at that, and that was 140. This is our mu sub x. And then our standard deviation sub x, we did the NP times 1 minus P. And that number, according to my calculator, was 9.54. Is that what it was? Yeah, 9.54. All right. This is my standard deviation sub x. So what I'm going to do is I'm going to equals. I can either calculate the z-score or I can just look at what 2 standard deviations above the mean is. That's what I'm going to do. I'm going to do 140 plus 2 times 9.54, because remember, anything more than 2 standard deviations above the mean is an outlier. So 2 times my answer plus 140. So I have approximately 159.08. So according to this right here would be my upper limit. Anything above 159.08 would be an outlier. Therefore, 162 would be unusual. This is our first way to calculate this. This is not my favorite way to calculate this, but if you want to use the mean and the standard deviation, this is how you would do it. If you're scared of binom, CD or PDF, this is how you would do it. I'm going to do it with binom next. So in your calculator, because this 162 is an exact amount, we'll use binom PDF. We have a sample size of 400. We have a 35%. And then we want exactly 162 successes. I'm going to use my calculator for that. Okay. 400.35, 162. I got approximately 0.003. Since that number is less than 5%, this is unusual. So unless my open math tells you to do something specifically, you are at liberty to do this however you would like. And maybe if you do it one way and then you're not sure, go ahead and try it the other way. Personally, I like having multiple ways to calculate things. But
Yeah, it's reassuring when you can check it with a different method.
exactly. I agree. I agree completely. I mean, the other way you could have found the Z-score of 162 and but I would much rather let's just stick with 2. I will not give you the third way. We're not going to do that. These are the 2 best ways to do it. Any questions before I give you another example? Y'all are awesome. You're doing great. Okay, let's do one more example. I want you to try this one. Okay, let's look back at the wireless only households. Remember, this was 41% was my success rate. In a simple random sample of 300 households, 143 were wireless only. Is this result unusual? Use whatever method you choose. I'm going to let you go and then I will quietly work behind you. What does it seem? I seriously give you 2 problems with the exact same final answer. I saw that and I was like, that can't be right.
I also had that. I was like, oh, did I screw something up? Did I just not change it?
See, I copied and pasted previously and just changed the numbers. I was like, was the calculator like not listening? It's possible. Right. Once you're all done, look up and see how you did. So the answer you would want to put words. Yes. Unusual. Whoops. If you can spell unusual. Usual. And see, it changed its color again all by itself. Right. It does that frequently. I'll be writing like in blue in class at the high school, and suddenly I'll be writing in red, and I'll, Miss Clyde, why are you changing the color? Like, I'm not, I'm sorry. It just likes to do that. It gets bored with colors.
Got to keep it interesting.
Exactly. All right, are there any questions here? Are we feeling okay? I'm hoping so. I know once you get into the homework, that's when you're like, wait, I had this in class. I really had this. And now I'm doing the homework and it's gone. But I'm hoping. And even if you have to send me 3 different problems for at least, I'm perfectly happy to help you out. Please don't think you're bothering me. This is what I do. I do this on purpose. I took this job on purpose. So we're still recording. So any questions that could help other students before we stop the recording? All right, I'm going to unrecord. Turn that off.